Good morning, good afternoon, wherever you are, whenever you are watching this. This is David Patiandi, and I am going to be telling you about what we call the structural elements in FLAC3D, which allows you to add things like cables and liners and things of that sort, and they're able to interact with the grid. Couple of preliminaries. Oh, here we go. This is what I look like. Um, Couple of preliminaries. I believe that the all of the slides that I have here and the data files with examples are obtainable. I believe you can obtain them apparently like next to where you're getting this or underneath where you're getting this. Also, if you have questions, you can type them into, I guess it's called the discussion pane. It's on the right-hand side and they will get to Itasca and they'll get to me, and I'd be happy to answer those questions. And obviously, since we're virtual, you can't ask the questions um, right now. So with that being said, there I am. You're going to get to hear my disembodied voice for the next couple of hours. Um, I've been with Itasca for a long time, since 1996. I spent a couple years at University of Toronto as a professor of civil engineering. Um, Other than that, I've been with Itasca. A lot of my work over the years has been with something called the particle flow code, PFC. Here's an example of a recent training course for the particle flow code. Particle flow code models movement and interaction of discrete bodies. They're usually spheres or polyhedra. And that's why you keep seeing these two tennis balls here as an example of PFC modeling. So the question then is, why am I the one giving the talk about the structural elements? It's because I'm the person at Itasca who developed all the structural element logic. I did that in the original version of FLAC3D back in 1998. That logic is still active. It's seen many new incarnations over the years, but I'm the guy who did it and implemented it and documented it, and so I'm the logical person to be giving this talk. But first, we have to start with a quote here. The late great eccentric Hungarian mathematician Paul Erdős once made the droll remark that a mathematician is a device for turning coffee into theorems. With that, here's my coffee. If you don't have any coffee, you might want to stop the recording for a moment and go get some coffee. So I'll take a sip of my coffee, and now we really will begin. Make this big. All right. So the whole idea of structural elements is to add these entities so that you can provide structural support. There are 7 different types of structural elements. There are cables, which should be obvious what a cable is. Hybrid bolt is a special cable that has the ability to cross a joint and provide a wedging type action. There are then beams, and there are piles, which are beams which can interact with the surrounding zones in a nonlinear fashion. There are then shells, and then different instantiations of types of shells, geogrids, which have only membrane resistance. They can interact with the grid, and then liners, like, for example, a shotcrete liner of a tunnel. What are these structural elements? They're actually finite elements. And so in the world of finite element terminology, we talk about elements, and elements have nodes, and they can interact with the grid, and they can also interact with other structural elements. And again, in terms of the terminology of FLAC3D for the grid, we talk about zones and grid points. So the question then is, why do we bother to use structural elements? Here's an example of a liner of a tunnel. There's symmetry in the 2 planes here, and actually in the 3 planes here. So here's a liner of a tunnel, right? We could just model that liner with zones, okay? But one of the issues is that zones are constant stress elements, and so they're not very good at modeling bending, because for bending you have a gradient through the thickness. You have compression on top and tension on the bottom. And in order to do a reasonable job of modeling bending, you would need many zones through the thickness, probably 7 to 10 zones through the thickness. That means that you would have very, very thin, small zones in your model, and very small zones are going to give you very small time steps. So not only would you have an excessive number of zones, but you would have very, very small time steps, which means you would have to take very large numbers of steps to be able to come to equilibrium. So with the structural elements, we idealize the structure. We either idealize it as a 1D type of element like a beam or a cable, or what we would call a 2D surface, which would be a shell. So here would be a shell, a liner in this case, um, interacting with the zones. So basically, if we're not interested in looking at very, very detailed, small scale local effects, like, if you have a beam that's shaped like an I section, if you want to look at the actual detailed stress distribution in the web, well, then you're going to have to use zones. But if you want to get the structural beam response, then maybe the beam is a strut that's holding some sides of a trench open, then you would use structural elements. So 7 types of structural elements. So here's my simplest possible problem that we're going to look at to illustrate these different types of structural elements. So what do we have here? We just have this big hunk of soil and we have a trench dug through this. Let's say we put in a cable on this wall going inwards, put a hybrid bolt on the other side going that way. We put a liner on the back side here. We put a geogrid into the wall over there. We have a beam that's serving like a strut across the excavation. And then we would have a shell. Think of it like a big metal thin shell that you put across there. Guys could walk across that or something. And then here we have a pile that's been driven into the soil. There's the surface. So the pile's sticking out and it's embedded down here. We're going to look at this problem. Okay. Um, Here's an example of just after we've done the analysis of having this thing loaded and deformed. What we're seeing here now are contours of displacement magnitude and also nodal displacement vectors. This guy right up here, every single node will draw an arrow that goes in the direction of the displacement with the length of the arrow scaled to the magnitude of the displacement. So you can see here, we just were pushing this on the top. It moves less and less and less as we go down. Okay. We're in this case, we're also showing the zones, but we're just showing them with their surfaces off. So they look like a wireframe because I want to highlight the structural elements and what they look like. There's just the same thing, but now we're turning on the surfaces of the zones and we're seeing the displacement magnitude. Like here you can see, for example, this beam is getting loaded with a uniform load pushing downward. So you can see how it's pushing down on the zones that it's hooked to on the sides there. All right. So what we're going to do now is we're going to actually build a FLAC3D model of this system. And as we do it, we're going to talk about all sorts of things about the response. So we're going to go into example projects. And first, we'll just run the whole thing. It says simple 7 complete. So I'm going to fire up FLAC3D. I've got FLAC3D set up on my Windows here so that the .prj, I can do this open with business and I can drill down to where FLAC3D executable is so that now all I have to do is double click on that. It's going to open up FLAC3D. We're using the latest FLAC3D, which is version 9 for this work. Okay, we're using version 9, subversion 159. That comes in the upper left-hand corner, tells you about that. So here's our data file. I've made this editor pretty big. It's 14 size, so I'm hoping that you should be able to clearly see the data file. All right, so we're going to go here. Our model new, we're starting off from scratch. Fish automatic create off. This is a fish thing so that it won't automatically create global variables. You'll actually have to define them as global if you want to use global variables. Here we're just setting some parameters to create the zones. And we're doing a few fancy things and reflecting it and deleting things and all that. We're not going to talk about that. I'm just going to put a return. Oh, wait, we just want to run this all the way through. Sorry. Let's just run this. So there I can run this thing. And I'm going to look at this plot item called My View. And there we go. It's cycling, cycled 4,200 steps. We're at equilibrium. And you can see what we've got here. We can see that this cable got pulled. That hybrid thing got pulled. There was a uniform pressure on top of that shell. You can see how it's deformed. I'm plotting contours on the deformed shape. I'm using the vector plot item to show those nodal displacement vectors. You can see the same thing for the beam. I have the zones here showing displacement magnitude contours. And I've also got the zones here. I've got them transparent. If it's not transparent, it looks like this. I want to be transparent so I can look at those structural elements more easily. Back here. Back here's my liner. It'll make you dizzy here. Sorry about that. Make it even worse. There we go. There's our geogrid getting pulled out. And there is our pile. There is our pile getting pushed to the side. Oh, here's an interesting thing. Look at this. Why are these guys not lining up with that guy? It's probably because I'm not drawing the pile. I'm sorry, I'm not drawing the geogrid in its deformed configuration. So let's take a look at this. So for example, that vector plot item, it's called structural displacements. Down here it says deformation factor 25. Let's look at the geogrid. Deformation factor is not checked. So I'm going to say deformation factor 25, hit return. Now you can see how they're both being drawn with a magnification of 25. All right. Here's another useful thing. If you go to view stats and you get the left-hand guy, hit it, you can always choose reset the model extent. And that'll put you back in a system where it's beginning to make sense to you. Okay. While we're talking about this, before we talk about putting on the properties, let's look at a couple other things here. Let's zoom in on this shell structure. So I've got a shell plot item, and we can look at the nodes. So it says marker. I'm going to say node, and I'm going to change instead of drawing a contour, I'm going to say label group. So there's the nodes. I can make them bigger and smaller. I say marker node size 3, 4, 5, 6, 7, etc. All right. What other markers are there? There's one that's called link. And these we'll talk about. This is the low level way that the nodes can interact with the zones. And so you can see there are links on those edge nodes that are linked to certain locations inside the zones. The structural elements essentially just get created and they will automatically link themselves to zones that they're in. They're linking themselves in a general way. They can be at any location in a zone. It has nothing to do with grid points. Okay. What else did I want to say for the time being? Let's look at system. Here is element system. This is the local element system for each of these shell finite elements. Red, green, blue represents X, Y, Z. Red, green, blue. That can, of course, be changed when you say system element. You've got X-axis. See, it says red. Y-axis, it says lime color. I'll call it green, right? But of course, I can change that, change it to blue. Now we can't see anything. Let's go back to the green. You get the idea, though. So, and of course, these can be scaled. Let's see, how do we do this? Scale target. This target means that it's going to be the size relative to the size of the screen. So if I do 0.15, they're a little bit smaller, and then I can see what I'm doing. So XYZ local element system. Okay, I think that's the only system we want. We'll talk about some more later. There's also a material system. If you use an orthotropic or anisotropic elastic body, you have to specify the principal directions of the material, the principal directions of orthotropy. So you could look at that system as well if you had that. And then there's something called a surface system, which is going to be used when we recover stress resultants or stresses on shells. Okay. And we'll get to that a little bit later. There's also, yeah, let's just leave it at that for now. What else did I want to mention? Let's look at my cheat sheet back here. Um, well, okay, let's start adding these as we go, and then we'll go back here. Okay. So now what I want to do, I'm going to shut this down. Just say discard. And now we're going to go back up and it's going to say simple 7 work. But first, yeah, let's do this. We're going to open test all cells simple 7 as a PowerPoint file. Okay. And let's talk about the different components in this model and what the properties are. Essentially, what you're going to do is you're going to create the elements and you're going to give them properties. And that's the extent of it, actually. So for this system, this really simple toy model, let's assume that we have an elastic soil. We're going to have gravity on, so we need to give a density. And so since it's an elastic isotropic soil, we just need to give it a Young's modulus and a Poisson ratio. Let me now fire this thing up, show you what that corresponds to. So I'm going to open, this is in the simple 7 work directory. I'm going to open up that project and that data file, and we're going to incrementally go through this. Here we go. Now I can talk about the data file. So model new, clear out the memory of FLAC3D, fish automatic create off, make sure that you have to actually define global fish variables. Here's some parameters that are going to control the zoning, the size of the zones, and the number of the zones. So I'll put a return there and I'll just run this. So let's look at this. So now we need to create, so we have a plot item we just created called my view. We didn't create that. Let's actually create one. So we would say file, new plot, and I'll call it my good view. There's my new good view, comes over here. It has no plot items in it. So let's add some plot items. Let's add the zone plot item. So we're gonna just click over here. We can choose the zone plot item, and there's our grid. I also always like to do a few things. I like to add the axes plot item so we can see what's going on. So there is our axes, just in case, make it clear. There's this item basically can be, there's a button here called fixed. Notice if I click on zone, I get the attributes of a zone. If I click on axes, I get the attributes of the axes. Fixed means it's going to stay on the bottom left-hand corner of the window. If you don't make it fixed, it's going to be at the 0, 0, 0 point in the global coordinates of the model. So that was my reference. That's my 0, 0 point for everything. Let's keep it fixed. We can see here the trench is oriented along the y-axis. In this case, Z is vertical. All right, there's our zones. Now we need to give them properties. So we're going to assign a constitutive model. That's the elastic constitutive model. Here's our Young's modulus, Poisson ratio. Here's our density. Let's do a return. See what it does here. You should be getting some interesting, nice messages down here. So zone C model assign elastic, model elastic assigned to 720 zones. And now we're giving these properties, property Young set in blah, 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 using the elastic model. So there we go. So we just created the zones. Now let's talk about creating the structural elements. That's what we're going to do here. First, we're going to create that shell that was in the very front that we were looking at. So structural shell, what's the command? I should be able to hit F1 when I highlight that thing that said struct shell. That puts me in here. Somehow it didn't actually go to the command. It should have gone to the command. Let me try. Just choose struct shell create and hit F1. There we go. I had to tell it more. So here's the create command. Okay, and obviously we're not going to talk about every single thing, but essentially we can just decode this. I can just tell you in words. So we're going to give a quadrilateral region that has 4 corner points, 1, 2, 3, 4. We need to tell it which type of finite element to use. We'll talk about that later, and some ideas of what to do. And then we need to tell it the number of segments to use to designate to that quadrilateral. So we're going to make a 4x4 grid on a quadrilateral. All the shell type structural elements are triangles. So this should create 32 of them. So we run it. Here it tells us what happened. It says 32 shell elements created, right? It was quadrilateral 4x4 of squares. That's 16, and they all get turned into triangles. That's 32. In the process, 25 nodes got created and 10 links got created. Let's take a look at this. So there's a plot item called shell. So I say plus structural elements. Here's all the plot items. They're basically going to be plot items that relate to the type of structural element. So I say shell, and there the shell appeared. Let's change its color. Let's first go to the zones and make them transparent. Now let's go to the shell and let's change its color. Oh, I don't know. Let me make it that color. There we go. Again, let's look at the nodes. So we can say marker node. And there we see there's our 25 nodes, 5x5. There's 25. It said 25 nodes. It said 10 links. So I can say marker link. There's my 10 links that got created. All that happened automatically. Okay. So there's my shell that got created. Now we have to, well, yeah, okay. So let's create the shell and then give the shell properties. Then we'll create the cable and give the cable properties, etc. So we can go here, watch this nifty thing. I'm going to select all that and I'm going to go up here and I'm going to hit comment out the lines. That's execute the lines. Here we go. Comment the selected lines. There's a comment. Those are the other creation commands. Let's just go through with the shells first. So you assign properties for the shells for all the structure elements in the same way that you do for the zones. It's the same style of command. Structural shell, constitutive model, assign. Oh, which one? The elastic one. Let's look at the properties of the shell. Here we go. Let's say it's going to be a concrete shell. We're going to do a simple thing. It's just going to remain elastic. We can also have plasticity in our structural elements. We'll talk about that later. This is attempting to be the simplest possible model that shows them all. So since it's elastic isotropic, it has to have a Young's modulus and a Poisson ratio. And because it's a shell, it needs to have a thickness. Okay. So then we're going to go back to this. So here we go, property, thickness, Young's modulus, Poisson ratio. Let's run that. And we see property thickness set to 0.2 meters in 32 shell elements, property Young, property Poisson. There you go. Okay. Let's take a look at those properties, see if they actually got there. So I'm using the shell plot item. Okay. And I can say color by label, and I'm going to say label what? Label will be property. Which property? I get the pull down of properties. See over here. These are the possible properties that a shell can have. So Poisson, there, shell property Poisson constant 0.15, and it's using this color here to show that. Let's turn off the zones. There we go. Label group shells. What about Young's modulus? 3 gigapascals. I think that's what we assigned. You get the idea here, okay? Thickness, 0.2. If we had different ones all over the place, then there'd be different colors for each of the different values of the thicknesses. So that's if you color by label. You can also color by contour, and then you can also say property. And then, for example, density, Poisson. Now, if we had varying properties all over the place, then it's going to be drawing a contour plot of how those properties vary. Usually we don't have that. Usually we just color by label and we look at the properties in that way. Okay. Let's go on with life here. Oh, well, let's just continue this last thing here for the shells. And then the other thing for the shells, I'm going to load that thing. So we're going to look down here after we've assigned right there. Structural shell apply, -1E5. So this is applying a pressure to the surface of the shell. The minus means it's in the minus local Z direction. So it's in this case, the Z direction is going up. This is going to push down. Okay. Um, that's the shell. Let's go on to the next thing. Now we're going to make a geogrid in that back left corner that was pushed into the wall. Okay. Um, and let's just that thing is going to be an elastic thing, let's say, and so therefore it's elastic isotropic. It needs an E and a nu and a thickness because it is a shell structure, but in addition it has this ability to interact with the grid. By the shell structure alone is only going to be basically rigidly connect itself to the grid. But now for specialized types of things like a geogrid, it's going to interact in a different way. So the geogrid here is going to have additional set of properties, which is an interface stiffness, which is shown here. Here's the idea. There's the zones. The geogrid is inside the zones, and this might just be one giant zone. It doesn't matter. It doesn't have to be along the boundaries of the zones. I've just taken this and drawn it this way. But here's my geogrid, and then it effectively has these springs on its nodes that are connected to locations in the zones. So therefore there's a stiffness. So this is the interface stiffness. This is a stiffness per unit area. That's why it's newtons per cubic meter, because typical stiffness is force over displacement. So that'd be newtons per meter. And this is newtons per meter over square meters. Um, and then this has the ability to have a cohesion, and then it may also break, and then it will have a frictional resistance. But again, to make it the simplest possible, we just have to give a stiffness and we have to give a cohesion. And here I'm giving a cohesion of an effectively infinite by making it 1e to the 20. Okay. So again, let's look at the geogrid creation. It's going to be very similar. That's back up top here. Structural geogrid create, and it's the same exact type of command. And it's going to put it, except this is going to obviously in a different place. And then, so let's just run this. Let's look at that geogrid, turn back on the zones. Now there's a geogrid plot item plus structural element geogrid. Presto, you can see that guy back here sticking in there. And what did it say? Oh yeah, we haven't actually, we go back up. There we go. GeoGrid, 32 GeoGrid elements, 25 nodes, this time 15 links. Just take a quick look at those links. GeoGrid, marker, link. There we go. 5 times 3 is 15. You can see there just in the locations where it's overlapping a zone. All right, all the same stuff applies to the geogrid as it did to the shell in terms of looking at the coordinate systems and the nodes and the properties and things of that sort. So let's assign those properties in our model. Here's our data file. So here we go. So again, same sort of idea. Geogrid constitutive model is an elastic one. We again, because it's a shell, have to give a thickness. For the elastic model, a Young and a Poisson, and then again, the coupling stiffness and the coupling cohesion. So this is just like what I showed right here. It's these 5 properties. All right. So you get the idea, run that, and it's telling me, oh, here we go, property coupling stiffness set to 1E7 and 32 geogrid elements. All right, that's the geogrid. Let's look at the liner, same sort of a thing, created in the same way. Let's just run it to there. Let's find that liner. Where is that guy? Let's get the liner plot item. And that liner's back there. All right. I just put it there. This isn't really very meaningful, but you get the idea. I'm just trying to illustrate a simple model. All right. So again, let's look at some properties. Now, what about a liner? What kind of properties does it have to have? Go to the next slide in just a second. Here we go. Boom. Liner. So again, I'm going to just say that the liner material itself is going to be concrete and it's going to remain elastic. So it has an E and a nu and a thickness because it's a shell. Now, again, a liner, it is going to basically be something that's up against, it's typically up against a surface. Um, Now it's going to have a normal and a shear stiffness. And the little illustration is this: I'm taking my hand. If you can do the same thing, take your finger, push straight down. That's the normal stiffness. Now move that horizontally. That's the shear stiffness. In almost all cases for real materials, the normal stiffness is bigger than the shear stiffness. So in this case, I'm making the shear stiffness 10 times smaller than the normal stiffness. Again, this is stiffness per unit area. That's why the units are newtons per cubic meter. There's also all sorts of other, do I have that here? No, I don't. Um, so that's the idea of a liner. It has many other properties as well, but this is just our simplest case right here. All right, there's our liner. Let's just uncomment this. Here's the liner here, just assigning the properties. I think you get the idea. Assign the constitutive model and give it all the properties. There we go. Hit return, run this, and you're going to see the same thing. 32 liner elements created, 25 nodes, 25 links, because every one of those nodes is up against the surface of a zone. So therefore, each one's going to have a link associated with it. All right, now let's talk about a beam. We're going to put a beam as a strut across that excavation. So that's right here. Structural beam. Let's just pull these back. There we go. So here, create by ray. You're going to basically give a beginning and an ending point and a length. You're going to give a direction, and then you're going to give a length of that direction to make a ray. And then how many segments? 4 segments. That's the number of beam elements to create along that ray. So there should be 4 guys get created. 4 beam elements were created with 5 nodes. Let's just confirm that. We look at the view and you'll get I bet you know what's coming up here, a beam plot item. And there's my beam. Let's go and reset model view because I've got myself kind of messed up here. Let's zoom in. There we go. Let's look at the nodes on that guy. Marker, node, boom. You can see, I don't know, can you see? There's nodes. 5 nodes, 4 elements. Looks good. Okay. Now, what about properties for a beam? Let's talk about that. So we're going to give the beam and the pile the same. We're going to both make them out of steel. And again, we'll just have it be elastic. Well, now this is a beam structure. So you have to give it properties of the cross section of the beam. That's what these 4 guys are. Let's look at the next slide. So you have to give it an area. So let's just assume that this thing is a circular cross section with a radius of 100 millimeters, right? So you're going to have to give it the cross-sectional area, pi r squared. You're going to have to give it the moment of inertia with respect to the y-axis and the moment of inertia with respect to the z-axis. Now that right away is telling you we have to actually then somehow define the orientation of that local axis because we're giving properties with respect to the y and the z. We'll talk about that more, but what you're going to end up doing is you're going to project a vector onto that cross-sectional surface, and that vector is going to be used to define the local y direction. And the local x direction is always going to be along the length of the elements of the beam itself. So that's going to end up being done. And then the last thing is we need to do a torsion constant to resist twisting. Okay, so yep, so that's it for the beam. And let's just take a look again at what that looks like. There's the creation of the beam, and then down below here is assigning properties of the beam. So again, Young and Poisson, because it's going to behave as an elastic material. And then here's these other properties we talked about: cross-sectional area, moment of inertia about the y-axis and about the z-axis, and the polar moment of inertia. And then this direction y. So again, that's going to define. So we're going to take the 0, 0, 1 direction. Let's look at our coordinate, our axes. There they are. So Z is upwards. So we're going to say that the local y direction is going to be upwards here, because that's what that command is doing. It's saying direction y is in the 0. So it takes this 0, 0, 1, which is just a vector in three-dimensional space, and it projects it onto the cross section. So let's see if it did that. Let's do return. Let's run this up to that point. There we go. And now let's take a look at the local element system. So we're going to zoom in here, and we're going to go to the beam plot item. Let's turn off the liner. Let's turn off the geogrid. Let's turn off the shell. There we go. And we're going to say beam, and we're going to say system. I think we're going to say system element. There we go. Red, green, blue is going to give us. So green is going to be Y. And let's, how do we do this? I want to be able to see that better. You can't see the red. Let's do beam group element. Let's change the color of the beam then to be, I don't know, yellow. There. Red, green, blue, X, Y, Z. So X is in the direction of the beam. We created this with a ray going from right to left. So that's going to define the local X axis. And then we had to orient the Y and the Z. So we said we said the Y direction is in the projecting this way. So that gives us X, Y, and then Z follows. So now we can specify those moments of inertia with regard to those two axes. Okay. Let's continue on here. Now we want to make a pile. Okay, so the pile is a structural beam, so it has all those same properties. Yeah, it has the same parameters, if you will. And then it also has additional properties, and I'm just showing some of them here. So it's going to have what's the perimeter of that thing, uh, what's that interface stiffness, and it's going to have, it's the plural stiffnesses, so a normal and a shear interface stiffness. And then it's also going to have a cohesion. The pile's able to basically have cohesion. It's like connected, and then it can break free. And after it breaks free, it has a frictional interaction. But we're just going to make it infinitely strong. So the interface cohesions, it has a separate cohesion in the normal direction and in the shear direction. It can break in shear. It can also break in moment in normal direction, and the gap can open up and things like that. All right. Uh, so let's just do the pile. It's going to be the same thing. Going to go back here. Well, the pile's down there. You get the idea though. Create by ray. We're going to do 8 segments. So let's make that pile. Here's the pile. Notice all those properties. So the first sets of 3 up here, those are the same as the beam. Notice you can use a space and then 3 dots, which means that this is a continuation of the line of a single command. And there's those things we mentioned, the coupling, the stiffnesses and the normal and the shear, and the cohesions and the normal and the shear. Right. So I say return. And there we go. All those properties got set, and it's telling me that right here. And again, the same sort of a thing. If we want to look, what are the properties on there? We go to that view. We add the pile plot item. There she is back there. And let's go. I want to make the zones not transparent. You can see it's sticking out of the ground. And what do I want to do? I want to look at the properties. So let's just go, same idea. Let's put the nodes on. Let's change the color of this thing for the pile. Now you can see those nodes. And then let's go for the pile again, label. And we want to do property. And then here's all the properties for the pile. Okay, all these different things. We'll talk about them later. But for example, moment of inertia about the y direction. Oh, how come it doesn't say the value? Label property, density. Gave me a density. Oh, cross-sectional area gave me a value. All right, interesting. So there's a proper moment of inertia about the Z gave me a value. I see I'm looking over here. What about moment of inertia about the Y? I think that's one that we did and it didn't give me. All right. I'm going to list that down. We'll get that fixed for some odd reason. It's not giving me the value, but everything else should be perimeter 0.63, etc. Okay. The last thing, we're going to create a cable and a hybrid bolt. Cable, these things are going to be made out of steel, for example. We're going to have them be elastoplastic. They can yield. They'll have a tensile yield value and they'll be elastic perfectly plastic. They'll have a compressive yield value, which could be different. So that's what this yield compression and yield tension are doing. And then the other things, they also basically can have a cohesion. They're firmly connected, and then they can break free, and then they're going to have a frictional interaction. Um, and so again, then when we talk about these properties, those grout properties, again, there's a stiffness of the stiffness at that interface. There we go. And we've been doing that. So let's just finish this. So there's the pile. And we're just going to see the same thing again. So the same way, creating a cable, creating a hybrid bolt. Way at the top there. Home. Here's where we're assigning properties to the cable. Here we're assigning properties to the hybrid bolt. So at that point, we run this. Let's just make sure we've got all these things. So that pile, let's change that color so we can see it better. There we go. So we're showing the beam. Let's make those nodes smaller. What do we got? We got the shell right up here. We got the geogrid back there. You see it? We got the liner opposite of the geogrid. And now let's add a cable plot item. Boom, there's my cable. Let's show the nodes. I think it's broken up into 8 elements. And then the hybrid bolt is called hybrid plot item, and it's over on the other side, right? Okay. Let's do again the nodes, and we can see that. There's our system. Now we need to apply some loads to make this interesting. So we have gravity on, so that's going to affect that's going to give us the gravity load in the soil basically. So we're going to say for the shell, we're going to apply a pressure to the top. Now for the geogrid, we're just going to take that outer row of nodes and we're going to apply a distributed force along there. And that's what this is doing, struct node apply force. So that is this guy. So GeoGrid, I don't want to show the links, I want to show the nodes. So that range is finding these nodes and we're applying forces on there. And we're applying forces, I think, in the global X direction because we're just pulling it out. Yes, a force 25 in the X. And that this range is just finding those nodes. The liner, we're just going to apply pressure on its face, pushing it inward. The beam, we're going to apply a distributed load acting downward. Um, uh, yes. And then for the cable and the pile and the bolt and the hybrid bolt, we're just going to basically apply a nodal force. We're going to find the node at the tip. And there's a helpful thing when you create the cable, it's going to create a group name for the node that's the first node, and it's going to create another group name called cable end for the other one. So thus, if I want to apply a force to the first node of the cable, which is the one on the surface, I can just say range group cable begin. And remember, every time you give a group, you have to enclose it in in quotes because it's a string. What are we doing here? This is fixing the grid point velocities of the entire bottom of the model. The model's at minus 1.5 meters. Turning on gravity. Okay, and structural elements. We have to specify damping, and we'll talk a little bit about this. We're going to use a type of damping called combined local. We're going to specify large strain. You always have to specify whether you're running in large strain or not. In this case, we're just running in small strain, so large strain is false. And then we're going to use the model solve command to a convergence ratio of 1. Okay, so now let's just go and put a pause in here. So it's going to do everything except start cycling. And when I hit continue, it's going to then solve. So I want to run this up to there. Look at my view. There it is. Oh, yeah. Well, let's just do that. And now we're just going to say continue. Oh, here's one other thing I like to always do. Up here in the left, I like to be able to see the total number of cycles that have occurred in the model. So to do that, we're going to go to legend, select legend, and these are attributes of the legend, and one of them is step. Notice what happens up here when I click on and off step, right? So mechanical step 0. I like to be able to see that. So now when I hit continue, it starts running the rest of the data file. And it's not very exciting because I'm not showing the deformed shapes, but just to give you an idea, let's draw the shell. Let's just focus on this guy. So we're going to go to that shell plot item, and we're going to say contour of displacement of node, and then which component or the magnitude. Let's just look at the magnitude. And there's my magnitude. Shell displacement 4 millimeters in the center, and then it gets to almost 0 on the sides. All right. Now let's look at the deformed shape. So again, I go to that same plot item and I say deformation factor, click it, and let's do 25. Now you can see how it went down. Now what you also see, let's do it even more. Let's do 50, exaggerated. You see how it's bending from the pressure link. Notice, see these guys over here? It moved down. Well, if we but that actually stayed on it's connected to the surface of the soil. So we got to also do the deformation factor of 50 for the zones that we're showing. Deformation factor 50. There you go. You see the whole thing moved down. That's why they were different, because we weren't doing the deformation factor. So of course we could do this for all of them. Just for example, let's look at that beam back here, beam deformation factor. Let's just do 25, and you can see how it's bending. And the last thing I want to point out, let's turn off that element system for the beam. What did I want to point out? Oh, that vector plot item is quite useful for the structural elements. So what we're going to do is we're going to go plus structural elements, and it's called vectors. And when it comes up here, it says structural displacements. Now you can see the vectors of this shell, but again, that's an undeformed configuration. So if I want it to match up, I need to give the same deformation factor. And then I need to actually tell this guy to refresh the screen. And there we go. They're the same. So you can see the nodal displacements. Same thing over here. If I met the same deformation factor for the pile, I'd see that as well. Okay. Let's see. What else did I want to talk about in this problem? Contour of displacement magnitudes. Oh yeah, we can also look at shear force and bending moment contours in the beam. Just to illustrate that, let's turn off a lot of things. Let's just focus on that beam. Turn off the geogrid, turn off the shell. There's my beam. And so I can say beam contour, and one of these is going to be bending moment magnitude. There we go. And what we've got is a high bending moment in the middle, and it's rigidly connected to the zones. So there's a reverse bending moment. There's also bending moment over here. Um, okay, and we could also look at the shear forces. And there's a convention as to what's positive and negative. We'll wait for the stress resultants because we're going to talk a little bit about that. But basically, what we get with the shell is what we compute are actually stress resultants. This is the result of integrating the stress distribution through the thickness. Um, and what these are similar to is it's similar to having bending moments. We're showing here the stress resultant My along this face of the shell. There's going to be a similar MX along that face. These are like bending moments. There'll be a shear force for the other resultants, and then there'll be a membrane set of resultants. We'll get to that in a little bit. Okay, let's shut this down and let's continue with the talk here. Okay, so there you go. In principle, you're done. You just need to understand the properties. You need to create these things, and then you go to town and watch what happens. But let's talk a little more about them so you get a better understanding of this stuff. So again, these are the primary types of structural elements, and the what I'm showing there that's circled are the basic type of structural idealization. So we have a cable, we have a beam, a pile's a type of beam, we have a shell, geogrids and liners are types of shells. Okay. Um, these entities themselves can be elastoplastic. The ones we looked at so far were just elastic, linear isotropic. Um, then these guys have a interaction with the grid that's cohesive to begin with, and then it can break free and then it becomes frictional. And that whole capability is provided by these things called links. And what these links actually are nonlinear springs. In the vast majority of cases, you don't even need to know about that, because when you create these elements, you first create the zones, then you create these structural elements, and it will automatically create the links in the locations of the nodes for the nodes that are actually inside these zones. Okay. But we'll talk about that so that you understand what those links are. So again, these are the basic structural members. Cable can be elastic or elastoplastic. And by that, we mean it can yield in tension or compression separately, but it's a cable. It cannot resist bending. Okay. Um, a beam is a typical beam structure. It's assumed to have a bisymmetrical cross section. Again, the behavior can be elastic or elastoplastic. And in addition, you can have plastic hinges that form at the nodal locations if you do things properly. Um, a shell is a structural thin shell. Um, so it has elastic behavior, and that can either be isotropic or orthotropic, or it has elastoplastic behavior. So that's the basic structural member. Um, then let's talk about how they interact with the grid. Again, the cable is interacting in the shear direction along the axis of the cable. Think of having grout around there. It can be cohesive, it can break free, then it becomes frictional. And in the normal direction of the cable, it's just going to be slaved to move in the normal direction with the zones that it's in, that are, so it just moves with the zones in that direction. But when you pull it in the shear direction, that's when all the interesting action starts happening. Um, Hybrid bolt is a special type of cable that can resist joint shearing. We got beams. By default, they're just going to be rigidly connected to the grid, um, and then a pile. So now we've got much more sophisticated stuff. Okay, so it is a structural beam. That's why it says beam. But in addition, it has this certain types of behavior normal to the pile axis and certain types of behavior in the shear direction. In both of those directions, it's cohesive and then it breaks free. It becomes frictional. And there can also be a gap in the normal direction. By default, the shell is rigidly connected to the grid. The geogrid then is a membrane shell, and it has behavior in the shear, in the plane of the geogrid, right? Again, it can be cohesive and frictional, um, and it's going to be slaved to the grid motion in the normal direction. And then your liner is a structural shell that can resist both membrane and bending loading. So it's a full-blown structural shell idealization. Um, Again, it has frictional and cohesive interaction in both the normal and shear directions. Um, it can build up tensile forces in the normal direction. A gap can open, gap can close, etc. Okay. Let's just look a little bit about the underlying theoretical framework of how this thing works. So we're doing explicit dynamics, okay, which means we're taking small time steps and we're cycling. Every time we take a time step, we're updating what's going on. We're updating the formed shape, and we're moving forward in time in that way. So let's look at this is a typical shell structure here. 4 shell elements. Let's look at this element E. So that element E has 3 nodes, and at each node, there's an internal force that's acting on that element. Okay, so it has these, I'll call these local numbers 1, 2, and 3. Okay, so every single element has its own set of internal forces acting on it. So what we do then at a node like this node is we sum up the element internal forces from all the guys that are so-called using that same node. Okay, that gives us the resulting force, F. We then use Newton's law to say F equals ma, mass times acceleration. And now we're going to make a finite difference discretization of this. So basically the acceleration is the change in velocity over the change in time. We can bring the m to the other side of the equation. It looks like this now. And now we're going to replace the delta v with the v at the end of the time step and the v at the beginning of the time step. Here we go. There's the change in velocity. Bring that over there is equal to force over mass times delta t. So this is letting us update the velocity. The new velocity is the old one plus this is that resulting force. Notice if all the forces at the node sum to 0, then the velocity doesn't change. Okay. Um, so what we're going to do then is we're going to, knowing the velocity, if we hit that with delta t, we get the displacement increment. Okay. Um, and then we got to get the forces again, those internal forces. So we're going to update those internal forces. Here's the new internal forces. Remember, those are the internal forces here acting on each element, by what we call a stiffness matrix. So we get the increment of each of the nodal displacements. We hit it with a stiffness matrix. What is a stiffness matrix? The basic idea here is it's from basic finite element theory. Here's a beam. It has 2 nodes. Each node in the structural element logic has 6 degrees of freedom, which means it has 3 translational degrees of freedom and 3 rotational degrees of freedom. So just for this little beam, we can relate the forces in terms of those degrees of freedom. So since there's 6 degrees of freedom, there's 3 forces and 3 moment quantities and 3 forces and 3 moment quantities here. So you get 12 of them. And here's the different displacements. These are the translational displacements acting on node 1. These are the rotational displacements acting on node 1. Here's the same thing for node 2. And this stiffness matrix is what relates. If you know what the displacements are, you multiply by the stiffness matrix to get the forces that correspond with them. And so that's going to look something like this. And it's going to have all these different terms. Like in the case of a beam, it'll be related to the cross-sectional area, Young's modulus, moment of inertia, all that kind of stuff. Okay. Um, in the case if you have a plastic material behavior, what you end up doing is you now have to create what we call integration points. And what happens is the stress gets stored at those integration points, and we end up doing this integration over the element volume. So we take those internal stresses, hit it with this what we call a strain displacement matrix, to update those forces. That's what happens in a plastic thing. And we're not going to take the time to talk about all this. This is the details of what happens during a plastic update. Notice at the end of all of this fun stuff, we get a new updated force. Okay. What I just want to point out here is we have three constitutive models available for the shells and the beams. So we have, if you had a steel structure, we have a von Mises constitutive model, and then to model, for example, concrete, we have a more Coulomb model and also a more Coulomb model with strain softening. Um, these are the same constitutive models of those names that are in the basic FLAC3D for the zones. The only difference is these are slightly reformulated to give the relationships for a plane stress system for the shells, and a similar type of thing for the beams. Key thing is when you're doing an elastoplastic constitutive model, you have to specify the layout of the integration points. And the basic bottom line is the more integration points, the better your solution, but the more runtime you're going to have. Um, let's just look at what I mean by this. Let's unpack this. Let's say we have a beam or a shell and we're applying moments on the end. So then we have a uniform, this turns into a smiley face. So we have a uniform moment distribution across this thing. There'll be no shear stresses. This is called pure bending. If we then look at, this is the thickness of that beam. So the thickness is in up and down direction here, right? So here's the applied strain. It gets shorter on the top and it gets longer on the bottom, which then corresponds to the stress. It gets a compressive stress on the outer fiber top, a tensile stress on the outer fiber bottom, and then a linear variation across. Now, as we start to approach the yield moment here, well, the strain still is linear. You just keep straining it more and more, but we start to get yielding. This is the yield stress, the axial yield stress of that beam. Notice how the yielding progresses inward from both surfaces. Okay, so this is the nonlinear behavior. This is what has to get tracked by those integration points that we specify through the thickness. The more we have, the better we can resolve this type of bending related stress distribution. Okay. Um, if you want to have plasticity in the beams, now you have to say, well, we assume we have a rectangular cross section for a beam, and then you're going to basically be specifying this integration point layout. You're going to say how many along a single, this is a single beam element, a single one. So along the action, how many? In this case, NX is 3, but you really only need to do 2 for most problems. And then here we're doing 3 in the local Z direction and 5 in the local Y direction. All right. You can also have a circular cross-section beam, and then you have to distribute the integration points as we show here. Here's an example to get some idea of how many integration points you need. We're going to look at a beam with 3-point bending, loading it by P. Okay. In this situation, what should happen, you have the maximum moment at the center and you have 0 moment at the two ends. And what will happen then in a beam, if it's made out of a structural steel, for example, is you will get what's called a plastic hinge, where you get a localized region where you reach the plastic moment capacity, and then it just keeps on forming a discontinuity in the rotation there. And this is what this looks like. This is an elastoplastic beam that we modeled of this situation. And here is the force at the center, and this is delta, the amount moved down. This has been loaded by applying delta. So we're slowly forcing this down, measuring the resulting force. And so here you see it reaches a plateau as it starts yielding through the thickness. And at this point, we're looking at, we have a plot item that can tell us the yield state. So here, these guys, this color, the light blue is never yielded. And then less than 50% is the green, less than 50% through the total integration points. And here more than 50%. It's yielded all the way through. And so we're seeing this localization. This is a plastic hinge. This is the integration point layout that we used to do this problem. You can see there's many beams along here. Each beam has this set of integration points. This is an example of the convergence of that problem for the beam. What are we plotting here? So this is the theoretical limit force. If it was a perfect plastic hinge, this is what E should reach when you form the hinge. This is the number of integration points through the thickness. We're going from 2 integration points through the thickness all the way up to 12. Um, and this is how it converges. As you get more and more, it begins to converge a little bit high of the theoretical solution. And if you use more beam elements across this, you then will pull this down to get closer to actually converge to the theoretical solution. An interesting point of behavior is you see that you're converging from below if you have an odd number of integration points, 3, 5, 7, and you're converging from above if you have an even number of integration points. Okay. Here's the same idea of an elastoplastic shell now. What you're going to basically decide is you're going to say how many integration points through the thickness. You can see the shell, see that mid surface triangle here, nodes 1, 2, 3. Here's the thickness. There's half of the thickness. There's half of the thickness, right? And so you're going to specify how many integration points through the thickness. And again, you're going to see a similar convergence type behavior. Here's the circular plate simply supported with a pressure applied to it, and that pressure is slowly increased. And here, as we add more integration points, we're converging to the exact solution. This is just an animation of that system. So what are we looking at here? How do I stop this thing? Boom. Okay. What we're doing is we're applying a pressure to the surface of this, and we have simple supports on the end. And what we do is we apply a small pressure, we go to equilibrium. We apply a small pressure, we go to equilibrium. And so then what we're monitoring is the center deflection. That's the x-axis. This is the applied pressure. And so as we go, here we're showing these guys have begun to yield. And the yielding starts in the middle because that's where the high moment is, and there's zero moment here. That starts yielding on the outer surfaces, the outer fiber. That's going to spread to the boundary, and then the yielding is going to progress from the center outward again, where it's gone all the way through the thickness. And so there's the first level of yielding partially through the thickness, and there's the one all the way through the thickness. And this then is the collapse load where we apply more pressure and it just keeps on deforming. All right, so that's elastoplastic shells. And how do I make this disappear? Right there. Okay, I'm going to take a break for a moment and get another cup of coffee. And I believe that Amanda is going to be able to edit this out. And so I will be back. I will just leave everything running. I will be back as soon as I come back with a cup of coffee. Okay. Okay, everyone. This is Dave Yandi. I'm back. I've got my new cup of coffee, ready to create some more theorems. Okay, let's talk a little bit about damping. Okay, so you have to specify damping for the structural elements. By default, there is no damping. So you're always going to have to be specifying damping. Damping is a mechanism to remove the kinetic energy from the system. So that's your command, structural mechanical damping. There's two kinds of damping, what we call local damping and combined local damping. The basic idea here is that the local damping is, think of a big system of nodes and springs. That's what your elements really are, nodes and springs. You hit that thing and it starts vibrating, and everyone starts vibrating separately. And what this local damping is going to go in there to each node locally, and whatever the unbalanced direction of force is, it's going to apply an external load and push against it. So like if you were one of those people, if you were a node and you were vibrating, it would be, I would be walking in there and pushing, adding a force to push against your head to slow you down. That's called local damping. You can read about it in the manual. And here's, oh, tennis balls. Look at that. So this system is like our structural element system. The nodes are the tennis balls and the elements are the springs. And so if we look at that, if we hit that and excite that system by hitting it with a tennis ball, there you go. You can see this thing bouncing around. Um, and so that's what is going on in the structural element system. And the damping is removing that vibrational energy. Go back. Whoops. There we go. There's also this thing called combined local damping, and this is going to be useful if we have systems where we sort of impose a uniform motion, like we're pushing on a beam or something like that. Here is just the section in the manual where this is talked about, and you can read more about it for the details. Here's just an example of a beam structure that has a uniform load imposed on it. And what we're monitoring here is the deflection of the center of the beam. That's the y-axis, and this is a number of cycles, step number. Okay. Um, the gray is the original structure of composed of 8 beam elements. Those are the nodes, and the beam elements, the undeformed shape is shown, that is gray. Then we added another plot item where we put a deformation factor on there. And so this is the deformed shape. And what we're seeing here is how the center deflection, it overshoots and then it goes back and it shakes around and eventually comes to a static equilibrium configuration. You're going to get different paths if you use different dampings. You can see the is not exactly the same dynamic response, but they will give you the same static equilibrium state, and that's usually what you're interested in. So we should be able to see this. Let's look at this example. It's called beam uniform load. So I'm going to go up a level, beam uniform load. There's a PowerPoint in there. This is just describing that problem. So it's a structural steel beam. We're going to have it be an Euler-Bernoulli beam. We'll talk about that later. That's your beam from simple beam theory. There's a Young's modulus, Poisson ratio, and then let's assume it has this type of cross section with the values given for A and B. It has a force per unit area, force per unit length that's applied to it. This is the theoretical maximum deflection. Okay, here's the moment of inertia about the z-axis. This is our local system. And so when we make this beam, we're going to want to have the local y direction be upwards. We're going to do that by specifying that y direction as a property. And so for this system with a 70 kilonewton per meter pressure, the maximum displacement is almost 12 millimeters. Okay, so let's actually run that thing. Beam uniform, fire it up. Da, da, da. It's a good chance to take a sip of coffee while you're waiting for FLAC3D to wake up. And so again, if you looked at my description of the problem, all of these parameters here are just going to be made global variables, and I'm setting this up so it's a parameterized model. And so here's all those things, the E and the nu, the L and the A, and then from that we can compute the moment of inertia about the different axes, the area, et cetera, et cetera. This is the theoretical solution. V naught equals then that. And here's the number of elements, beam elements. Whole data file is right here. Very simple. We create a beam and we give it nx is 8. We give it 8 elements, 8 segments, right? We assign the constitutive model to the beam to be elastic. Here's that y direction thing. So 0, 1, 0. So we project the global y direction is going to be the local y direction. Here's my global coordinate system. Okay, so I want y to be aligned with the global y. That's cool. Here's the other stuff you need, the cross-sectional area, et cetera, et cetera. So at the beam begin node, we set the x velocity to 0, and then we set the y velocity to 0 at the beginning and the end. That's these condition here, right? They're both set to 0 there, and only the y is set to 0 there, right? We're applying a pressure loading in the to this guy here, and we're monitoring a history of a node. What is a nodal quantity we're monitoring? It's the displacement in the y direction. That's the global y direction. And which node? It's the node at 0, 0, 0. Notice our global coordinate system starts at the center. So 0, 0, 0 will be the center node. Okay. We're going to run a small strain analysis because that's what the theoretical solution we have is for. We're going to use local damping. Pause, look at the system, and then we're going to solve to a convergence. And then we'll talk about the rest in a minute. So let's run it up to the pause. Here's the view. There we go. We got the beam uniform plot item. Okay. Here's my center deflection. Here's my step. I got the history on top of this so we can see everything. Just watch here. You're going to see now the history as this thing goes down and overshoots and eventually reaches an equilibrium point. Notice I got the steps up here. I got that by going to legend, checking the step box. All right, enough said for that. Now let's watch it. Watch this. Watch the deformed shape and the deformation as we run it. There it goes. Comes to an equilibrium. Convergence. Okay, let's just run that one more time because it looks pretty cool. Watch, you can see the deformed shape and the center deflection. See how it overshoots, and then it comes to an equilibrium. Okay, let's go back to this. So, fish, there is fish access to all the different things related to structural elements. Okay, so these fish functions are going to be related to the components. So they're going to be related to nodes, and they're going to be related to each type of structural element. And then there's going to be some that apply to all structural elements. So for example, the ones that apply to all structural elements, connectivity, that's the connectivity. What are the nodes used by a particular element, right? I want to delete a particular element, struct.delete, right? These are the ones that operate on beam type elements, right? Struct beam.force. What's the applied force? This is the unbalanced force on a beam, right? Here's the guys that act on nodes. What's the applied load on a node? Okay. Here is an example at this one. In this example, we're going to say, this is the example we were running. I've lost my pointer now. Just a second. Come on, where's my pointer? I don't see my pointer. Oh boy, let's see, escape. Okay, what's going on here? It's because of this, I think. My system got confused. Yes, now I should have my pointer back. Sorry about that. Here we go. So I want to find the node that's nearest to 0, 0. So I can say struct node near, store that in a variable. And then I can say, I want the displacement, the nodal displacement in a global coordinate system of that node. And this is the degree of freedom. So that's the y displacement. That would be mid-disp. And so that's what I did in this data file. This over. That's exactly those same lines. So I'm going to then print out the value of the node. Which node is it? I'm going to print out its middle displacement. And then I'm also just going to list the displacements of all the nodes and make sure they're all the same. So here we go. Node pointer, struct node near 0, 0. Node number 5. Let's see. Is that node number 5? Here are the nodes. Turn that off. Here are the nodes. If I go to the question mark, I can select a node and see it says, see that question mark on there? So I click on that. Oh, that's structural element node 5, and here's all the data associated with it. Okay. Also, while I'm in this mode of this question mark mode, notice over here, the information box is also showing me a selected set of information. You probably can't read it, but right now down there it says 5, and then when I go here it says 6, and then here it says 7, etc. There, click on that one, structural element node 7. Or I can say, click on that one. That's the actual, not a node, but that's beam structural element 5. And here's all its properties and things. Okay. So returning to this, midpoint displacement, there we go, 11.98 millimeters in the negative y direction. So if I look at node number 5, these are the nodes 1 through 9, da 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 da. There it is, the y translational displacement. Da 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 da. Okay. I think that's all that I want to show of this. Yes, that's all I wanted to show for that. So let's shut this down. Let's go back to this. Sorry for this. In that whole process, I jumped out of slide mode and I did this. Here we go. And we've done all of these little things now for that example, so we can move on. So let's now just go through the basic parameters of each of these guys and the basic physical behavior of each of these guys. There's an example modeling a shotcrete line tunnel. Here's a retaining wall, looking at it from the side. There's a big trench. There's a pile or a liner. We're going to find out that the liners can also be in a special mode called embedded, and then they're actually going to be embedded inside of zones. So there's the force distribution on the either a pile or a liner. Here's a beam acting like a strut between these two sides, right? There's a more fancy picture of the same thing. There's the strut. I'm not showing piles or liners in this. Here's the liner, bunch of those shells wrapped onto the surface of that model. Here's a bunch of cables supporting a tunnel. Here's a bunch of geogrids. There's a lot of soil off to the right, but this is a free face. And so we just put in some geogrids and then we run this thing and you can see how the geogrids get mobilized and they help sustain the reinforced embankment. Okay, a little bit more under the hood. How do we connect structural elements to the grid? Again, this is happening automatically, and only in very specialized cases are you going to have to do anything with these links, but you should get it. It shouldn't be magic to you how the code works. So here's what it's doing. Here's a collection of 9 zones. I'm just drawing this in 2D to get you the idea here. And this is a cable that's been discretized into 4 segments. So there's 4 cable elements. The black guys are the nodes, and we're going to look at this guy here, okay, that node, and this is loaded with an external force of P. We're pulling on that cable. So looking at the center zone, expanding it. What is it doing? This node is getting mapped to, I'll just call it a local position inside that zone, okay? And at that position, we're going to continually know what is the velocity because the zone gets its velocities at its 4 grid points, but we can interpolate to get the velocity at this target position. Okay, so we have a link there that's linking the node to this location in the zone. Okay. And this node could also be linked to another structural element node, but in this case, it's linked to a zone. What happens then is that each structural node has its own local coordinate system. Okay. And so in this case, because it's a cable, what's going to automatically happen is that the local coordinate systems of all the nodes on the cable are going to be oriented. So X, I'm using prime to denote the local system. X prime is always going to be directed from the beginning to the end of the cable along the axis. And so in this case, then Y prime and Z prime would be normal to that. Okay. And so in terms of this system, there's 6 degrees of freedom. There's 3 translations and 3 rotations. Okay. Um, each of those 6 degrees of freedom can either be free, rigid, or deformable. And what that means is in that direction, free, it doesn't do anything. Rigid means it moves with the surrounding material. And so in this system, in the Y prime degree of freedom direction, this link is rigid, meaning that any motion in this Y prime direction of the zone, this node just moves with it. Okay. But along the axis of the cable, in this degree of freedom, there is a nonlinear spring that's behaving like the grout. So that nonlinear spring has a stiffness. So here we're looking at the force in the spring versus the displacement, the pulling displacement in the spring. It has a stiffness. That's why this has a constant slope. That's the slope. And then it has this ability to break, and then and it has the ability to slide. And so this is the frictional, there's a frictional component here that's meant to show like a frictional rheological component. Okay. So let's not talk about the physics of each of the structural elements. Okay. Um, so there's the behavior of the element itself. So here's the idea. I'm not going to read all these things. You can look at these yourself later. All of this is taken also from the manual. Um, there's your cable element. It only has 2 degrees of freedom locally. It only knows about stuff along its axis. Okay. Um, just for the cable material, notice it can go in tension. And if you start pulling it, it goes in tension. There's the slope. These are the parameters of the cable material itself. Young's modulus, cross-sectional area, tensile yield value, compressive yield value, and you can see them all here. There's the slope of this in tension. You keep pulling it in tension, it reaches its yield. It's elastic, perfectly plastic. You start moving it backwards, it starts unloading with the same slope. You start moving it forward again, it goes up and it starts going like this. And the same thing is happening in the compression direction. Okay. This is just a illustration of the idea. Notice you've got a cable, you've got conceptually a layer of grout, and then you've got the soil or rock around that. Okay, you pull on this. This is what it looks like. There's the grout. The grout is like an elastic thing, but then it can also begin to frictionally interact. Okay, and there is a confining pressure from the zone that's acting on it, right? And so now here's 3 additional parameters. This is how the cable is interacting with the soil or rock. So this is the force, the shear force in this material. Think of it as the force carried in the grout here. That's the shear force that the grout is exerting on the cable. So that's going to go up. There's the stiffness of the grout linearly, and then it's going to reach some maximum critical maximum value and be elastic perfectly plastic. Okay, what is that maximum value? That maximum value is going to be a function of the cohesion of the grout and the friction angle of the grout. So this now is sigma m. That's the confining stress. This is the perimeter of the cable. That's why it needs the perimeter. You take this, that's the compressive force. And so the friction angle is going to give it more and more strength depending on what the friction angle is. And here's the cohesion. That'll affect it if you go in tension. Okay. So that's the grout behavior of the system. This is just another way of trying to represent the picture. There's the cable nodes. There's these little springs in the shear direction. That's the cable itself, conceptually as a spring. Okay. Um, so there's then 16 properties of a cable. I'm just listing some of the first ones here. Okay. The manual discusses things to do to estimate the properties of the grout. Okay. There's also the ability to apply a pretension to these cables. Okay. Um, Now we come to the beams. Okay. So here's a beam element. It has 12 degrees of freedom, 3 translations, 3 rotations. Um, there's 2 types of beam elements. Call them Euler-Bernoulli, which is the beam element from simple beam theory, and then there's a Timoshenko beam element. The difference is shown here. For the Euler-Bernoulli element, this is for essentially simple beam theory. The idea being that if this is the beam and it's being bent, this is the orientation of a line that used to be vertical, perpendicular to the axis. And notice that when the beam deforms, this is a straight line, it stays straight. If you have a thicker beam, then what actually happens is that line that started out straight actually deforms because of transverse shearing that's happening on it. Okay. Um, this type of behavior is handled by a Timoshenko beam. Um, this would be something where you have a beam, let's say you have a beam that's only 4 meters long and it's 1 meter thick. That type of beam is going to have transverse shear effects. Um, so then you would need to use a Timoshenko beam. For most cases, that's not the case. Usually you have beams that are much longer than they are thick. And then that can be an Euler-Bernoulli beam. Okay. Um, each beam element then has 15 different properties. For example, moment of inertia is in the Y and the Z. This is again the way in which we orient the local Y direction by giving this global vector that gets projected onto the cross-sectional surface. Okay. Um, this is just showing the sign convention. These are right on the ends of a beam. There's going to be a moment. Think of it as a bending moment. There's also going to be a twisting moment. Here's the axial pulling force A. There's the shear force. And this is showing in terms of the local system what's positive and local. This is local XY. This is local XZ. It's telling you what's positive. For if you want to interrogate these forces and shears, you can do this by listing stuff. You can get it from fish and you can get it from the plotting as well. Okay. This of course is also discussed in the manual, this beam local axis system to give you the forces. Now we have a pile. A pile is a full beam structurally, but then it also has this interaction with the grid. Okay. Going back here, I'll go back a couple slides for a minute to the beam. The beam is just rigidly connected to the grid. Rigidly connected to the grid means that the entire translation of that node that's connected to the grid is just slaved to the translation of the grid. And it's free in the rotational directions. A grid is a volumetric thing. It doesn't have rotation. So those are just free. The pile though, um, sorry, there you go, has this additional interaction. So again, this is what I mean by the shear behavior for the pile. So in the shear direction, again, it has a shear stiffness, a shear cohesion, and a shear friction angle. And again, this is just like for the cable. It's exactly the same as we went through for the cable. In addition, it has stuff in the normal direction. This is a cross section of the pile. You can see that it might not be a straight line. There might be two joining at some angle. This is the average of those two normals. In this direction, this is the normal displacement that's occurring normal to the pile cross section. Same sort of a thing, cohesive and frictional. There's the cohesion, there's the friction angle. This is the compressive load. There's the perimeter, right? It goes up, loads up to a maximum normal force. perfect plastic unloads, and then depending upon a property called gap, you can actually have it maintain a gap and keep track of that gap. Okay. A pile, it has all the properties of a beam, plus it has these properties of how it interacts with the grid. We call these coupling springs. Okay. And in addition, you can also make the pile behave in an even more complicated way. So it behaves like a rock bolt. So then there's even more additional properties. Um, and so this, like, for example, it says you can have strain softening in the grout, you can have tensile yield, you can have rupture of the element as well if you do a rock bolt. Makes an exceptionally crazy model because it has 33 parameters then if you use the full-blown thing that's also a rock bolt. Here's the biggest important issue is how do you choose these stiffnesses for these systems? This is the interface stiffness. Um, what you're going to do is you need to choose that stiffness large enough so that you don't get a huge amount of relative motion between the pile and the zone. So here's my example. Here's my pile. It's being loaded this way. Let's assume that the stiffnesses were so low at these for these guys that it just moved this much. This would be bad. Um, this would be too much overlap. What you want is this amount of displacement to be small. Okay. One way to estimate that is to use this relationship here, which is described in the manual at this location. And what this is doing is it's basically coming up with an estimate of the stiffness of the zone that it's in. And this is the bulk and shear modulus of the zone, and that is the thickness of the zone. And this gives you an estimate of the zone stiffness, and you're going to basically make this thing about, I think the idea is to set it to be 10 times bigger than that. So this is what people would typically do. And then when you run your model, you need to take a quick look and make sure that you're not getting a huge amount of relative motion between the zone and the nodes of the pile. Okay. Here's a structural shell. Again, this guy by default will be rigidly connected to the grid. It has 18 degrees of freedom now because it has 3 nodes, 6 degrees of freedom at each. The piles only are suitable for thin shells. They're thin relative to their span, and that means it's the same sort of idea between thin and thick. So this is what we call Kirchhoff plate theory. So these shells satisfy Kirchhoff plate theory. Again, for most situations, that's what you have. Again, but if you only have a plate that's, a square plate that's 3 meters by 3 meters and the thickness is 1 meter, well, that's not going to be well modeled by a thin plate, by a thin shell, I mean. Okay, you would need to model that with zones. Um, Here's the key thing. There are 5 different finite elements that you can choose from. Basically, we have 2 elements to model membrane behavior, and then we have 1 element to model bending behavior. And then what we do is we lay these elements conceptually on top of each other. So you have the DKT plus the CST and the DKT plus the CST hybrid. Um, and I'm not going to talk anymore. Again, the manual discusses these things. Um, and this is an important thing. This is telling you that for problems in which a shell element is connected to the zones, you should use the DKT CST element. For other problems, use the CST hybrid with the DKT. Therefore, the default type is the DKT CST element if you don't give a element type. So the shells have simply these 3 properties: density, thermal expansion, because we can model thermal behavior with the structural elements. Basically, we can give them temperature increments and that will produce strains. Those strains will then produce forces. It can get the temperatures from a thermal analysis of the zones if you have thermal active. So you have to have thermal configured on. I think that's an optional feature, but if you do that, there is an ability for the structural elements to also have thermal behavior, but you can't have thermal flow through the structural elements. Okay, this again is discussed in the manual. Um, so here's an example of a structural shell, uh, fully fixed along the four sides with a uniform pressure. You can see the cool deformed shape that you get. Now let's talk a little bit about the types of responses that you get in a shell structure. Okay, so here's our little hunk of surface. So here's a shell, it has thickness T, and here's a local XYZ axis. Z is normal to to this, okay? Um, so stress is a three-dimensional quantity, right? So here's all the stress components. And notice that because it's a shell and it's a thin shell, it has a plane stress assumption. So sigma Z is always going to be 0, but you have these other stresses, okay? What they do in the shell theory is what you do is you integrate these stresses through the thickness to come up with what we call stress resultants. And we have three different types of stress resultants. We have the stress resultants that arise from bending behavior. Okay, so notice if we integrate, look at this one, sigma y. So sigma y, if we're bending this thing to make a smiley face like this, you're going to get compression on the top, tension on the bottom. If you integrate that with a moment arm, you get a moment. So we call these bending stress resultants. We also have transverse shear stress resultants. That's the shear stresses integrated through the thickness. And then we have membrane. Just for the membrane behavior, we have stress resultants. So there's 8 of them. What do they look like in terms of sketches? This is the MX stress resultant. And you see it's basically, these things are moments per unit length. So you have to take this and multiply this one by dy to get the total moment acting on that face. So that's the mx one. It's the moment acting on the x-directed face. This is the moment acting on the y-directed face. And then in the world of shells, there's also a twisting moment, which is shown like this. Okay, and this is symmetric on both faces here. I'm trying to show this. This is a desk outside of my office, and there's no support here. So if you were to sit on this, you would get this twisting effect. That's what this MXY is measuring. They call it the twisting moment per unit length. Here is the shear force per unit length on the X face, shear force per unit length on the Y face. So there we go. Those are now we're going to draw them. We're going to use double arrows to represent a moment and the direction of the moment. Wrap your right hand around those double arrows. Put your thumb in the direction of the double arrows. That's the direction of the moment. Okay, so that's those. And then for the membrane behavior, there's going to be, again, force per unit length on the X face, force per unit length on the Y face, and then a shear NXY, shear force per unit length. Okay. Um, so this is what you get when you use a shell theory. This is what you actually get out of the shell theory. This is what you compute in terms of the stress field. You compute these resultants. If you have like beam theory, what you're used to, you have bending moments and you have shear forces, and then you have axial force. That's what these collapse down to if you take the shell and turn it into a beam. Okay. Um, So what we actually compute is we compute stress resultants. And then what we do is we get the actual stresses and how they vary through the thickness based on these expressions here. Red are the stress resultants. Some of these expressions vary with Z. So here's the example, bending in the Y, smiley face, again, apply a moment, com tension on the top, compression on the bottom, linearly varies. So sigma Y is given by this. This is the my, the moment on that face. Okay. This is just like in beam theory. This would be m times y over I. That's what it looks like for the shell. And then there's also this guy from the membrane. So it's got a membrane effect too. That does not vary through the thickness. And then there's similar expressions. Here's how the shear force is produced. This is the shear stress, 0 on the outside, and it's a parabolic variation. Okay. So the key thing is that you compute the stress resultants and then you use these relations to get the stresses. And this is all expressed always in terms of the local, some kind of local coordinate system. Okay. Um, it turns out that these stress resultants are not needed during the computational process. You can end up getting what you're really doing there is you're getting those nodal forces and you're moving the nodes. Those nodal forces do not need to compute stress resultants first. So what we do is during cycling, we never compute stress resultants. We only compute them at your request. And so you have to give a command. You're done cycling. Now you tell it to recover. You either recover stress resultants and then after you've recovered stress resultants, you can recover stresses. Okay. Um, that means we have to have a consistent surface coordinate system for a collection of shell elements. And you do that by giving this command, structural shell recover surface. So here, for example, is if we did this, structural shell recover surface, what it's going to do is you need to give this is a vector in global space, and it will get projected onto the surface of each element, and then it will align the local x direction with this direction. So if I make, again, local x direction of the surface system, red, green, blue, notice if I do recover surface and I give it a 110, so that means that vector is this way. There's x, there's y global. I give it 110. Now the local x's are all aligned in that direction. Okay. So this is you need to establish a consistent surface coordinate system before you do the recovery process. Um, and then it's recovered in terms of that system. Now we can display these stress resultants and we can also display the stresses using the appropriate plot items that you see there. Okay. Um, and there's one additional issue related to that, which is there's a little checkbox here when you're plotting contours of stress resultants. It says use engine. Okay. Um, when you give the recovery command, structural shell recover resultants, it then stores that inside of the FLAC3D model. And then you can access that with fish. You can list it with a structural shell list command. Okay. Um, that's the data. It's using the engine stored in the computational engine. Okay. If you don't check this, then what it's going to do is it's going to say, okay, now you have to provide, this is called the surface X vector. This is the vector that gets projected onto the surface to align the local X direction of the surface coordinate system. So you have to give this, and then what it will just do is the plot item itself will do this stress recovery. It'll create the surface system and pull out the my value. You typically would use this if you're cycling, and you want to watch the plot update as you're cycling. Um, Usually this is sufficient, but sometimes you have complicated situations where you might have a liner that intersects another liner um, in some complicated way, and then you may need to locally establish these surface systems. So when you give that structural shell recover surface command, you can give it a range. So you can operate on a certain chunk of shells to make a surface system that looks like you want, and then you might want to operate on a different set of shells to get that surface system the way you want. Okay. Um, so let's just take a quick look at this thing. So here's an example called infinite strip. So we're going to go here into the example that's called infinite strip. This is described in the manual. It's one of the verification problems. And here's the basic idea. It's a long strip with A greater than B. It's simply supported and it has a pressure. Okay. And for that problem, we have a theoretical solution for the displacement field and for all the different stress resultants. Okay. And when we load that, it's going to look like this. It's going to deform. Simply supported on the sides, it's free on the ends. Okay. And here's the deflection as we go across the distance.
This is the Y direction. So the deflection is 0 on the ends, maximum in the center. There you go. Here is the moment in the MX stress resultant. Here's the MY stress resultant. Here's the QY stress resultant. That's discussed in the manual and compared. Let's run that just to illustrate this idea of the surface coordinate systems. Time to take my sip of coffee while it gets ready to go. Okay, quite small data file. This is basically like that uniform beam problem, but this time it uses shells. I'm not going to go over the details, but notice at the end, it's going to do after the solving, it's going to recover stresses, giving a surface coordinate system that's aligned where the X direction is aligned with the global X direction, and then it's going to recover the resultant. So let's just run this. Now, before I solved, I had a pause. So here's my system. And now I'm just going to say continue. And there it goes and bends down. And here we're monitoring the displacement of the center node, the deflection, and it's cycling along. And now it reached the convergence we wanted after almost 13,000 steps. And you can see it just like that beam, it overshot. And then the damping brought this down to a to a static solution. Let's just look at that one more time because it looks pretty cool. You can watch it go down. Okay, now let's look at the displacement field. So I've got this shell, I'm plotting group of elements. Let's do a copy and paste of that particular plot item. So right up here, copy, paste. There's my new one. Turn off the old one, look at the new one. Let's do contour, color by contour, label, displacement of node, magnitude. There we go. Maximum displacement, 48 millimeters at the center, 0 at the sides. That corresponds with the theoretical solution. Okay. Now what else did I want to show here? This is the one. Okay, let's look at a contour of the bending stress resultant MY. So let's look at the surface coordinate system. So let's go back to this guy and let's say marker node. There's my nodes, and then do system surface. Now, can't see this very well. Let's see. Let's make the surface system bigger. System surface 0.04, 0.06. Red, green, blue. So red is the X. Red, green, blue. Okay. And that X here, it corresponds with the global X there. And that's because we did this structural shell recover surface 100. It projected 100 onto each element and aligned the surface system so that the local X was aligned with the X. So now, since that's the X, the green is the Y, the moment per unit length is going to be the moment along here, the bending that is accompanying this deformation here, turning it into the smiley face. So we go back to this and we say contour and we say resultants, boom, and let's say use the engine data, and that's NX, that's the membrane resultant. There is no membrane loading here. MY, there we go. This is in the surface Y direction. And again, it's a high value in the middle. It's nearly 0. It like flips sign a tiny bit. This will approach 0 exactly if you refine the grid, and we discussed that in the example problem. Okay. Similarly, we can look at stresses, stress elastic. Now there's no stress elastic because we didn't recover the stresses. So we're going to run this again, or we're just going to say struct shell recover stress. But now hold on, stresses vary through the thickness. Okay. So if you remember, These are the expressions of how to get the stress if you know the stress resultants. And there's a Z in there. They vary. See this? They vary through the thickness. So I need to tell it I'm going to make a contour of stresses, but it's only going to be valid at a certain thickness. Okay. So the way we do that is we give what we call a depth factor. Depth factor of -1 is the bottom surface, +1 is the top surface, 0 is the middle, and stuff in between is linear interpolation between. So I got to say structural shell recover stress depth dash factor 1.0 outer surface. There we go. Struct shell list question mark. Struct shell list stress. Stress. There we go. Let's just look at the range component ID 1 to 3. Stress at recovered depth at centroids of elements with an elastic model expressed in global coordinate system. There's the stresses, the X, Y, Z, Z, etc. All 6 components. Notice the SZZ is always 0 here. The stresses come back in a global coordinate system. And so again, we can then look at that with this plot item. There's the XX stress in the global X direction. Let's look at the one in the global Y direction. Again, outer fiber stress, 2.5 E6, it's near 0 there. That's the outer fiber stress from the bending. If we switch the depth factor and do it again, we should see a negative value instead of a positive value here. Okay. I'm not going to do that in the interest of time. We're just about done. We're just going to do one more thing we're going to talk about. Sorry about this. Here we go. Oh, wait. Still got to talk about these other 2 things. The geogrids. Okay. So it's a membrane. It has no bending resistance. And here's the idea, right? You're pulling on it and it has these shearing forces that develop along it, and it's got a confinement acting on it. And so here are its properties. It has a stiffness, a cohesion, and a friction, just like for the other systems. Okay. It has then these properties here. Okay. Cohesion, friction, and stiffness. There's this large strain sliding. If you actually run a large strain model and you want to pull the grid through the zones, the nodes will migrate through the zones if you set that large strain sliding on. Again, to get the stiffness, you can use the same expression that you did for the liners. Now let's talk very briefly about the liners. Here's the idea. That's a surface. There's a liner. It has shear stress acting on it. It also has normal stress acting on it. There's the idea. It's part of a shell structure. It has a local tangent plane, right? So this is how it interacts with the grid. This is the normal stress versus relative normal displacement. So it has a normal stiffness. It has an ability to fail in tension, and then it will go to 0 force there. Here's the frictional shear directional behavior. Again, the only twist here, so there's the shear stiffness, the maximum shear force, there's your cohesion, there's your friction, but after it breaks, it might have a residual cohesion, okay? Because it has the ability to break in tension. So the liner has the properties of a structural shell, plus it has these additional properties. And it also has the ability, you can turn on embedded, and then the liners can also be embedded in the grid. So that would be used to model a sheet pile, for example. Again, here's how you want to choose the stiffnesses. And the last example, very simply here, again, these are both in the manual. So what we're going to do is we're going to make an advancing tunnel going through the zones, going through the soil, and we're going to put a liner on it as we go. Okay. There's 2 examples in the manual. One of them is the simple example, which we're going to look at here, where we use shell elements, and therefore the shell nodes are just going to be rigidly connected to the zones. Okay. If we did the exact same thing but used liner elements, now you're going to have the ability for that interface to slip and separate. Okay, we're just going to look at this one. So here's our properties. It's a circular tunnel in a soft elastic soil. The liner is going to be shotcrete. It's going to remain elastic, and it's going to be rigidly connected to the soil. So we're using shell elements. Um, and so what we're going to do, we're going to excavate the tunnel. We're going to let the stresses redistribute. We're going to add a liner. We're going to let the stress move again in excavation, continue on in that process. Here's the idea. We've already created this and given group names to the zones, section 1, section 2, section 3. That's going to allow us to excavate and null zones as we go. There's quarter symmetry in this system, so we're just looking at this. Okay, here's how we add a liner. So it's already been excavated this far, but we haven't let the stresses redistribute yet. So then we put on the structural liner with this command. Structural shell create. This time we're saying create by zone face. And so we're basically giving the range of these zone faces, and that's where this shell then gets connected on. All those nodes then automatically get those links that are going to be rigidly connected to target zone locations. Okay. So then we can do this, right? We're going to monitor the displacement right here in the middle of this thing. So what we've done at this point is we've excavated the first section and let it redistribute. Then we excavated this, and in this case, we didn't put in a liner. So the additional deformation due to the second excavation is shown here. This crown is going down by 12 millimeters of closure. That's what we're plotting here, minus 12 millimeters as we get the equilibrium. If we put in this and do the same thing, now it only goes down 1 millimeter. And you can see the difference in, there's a lot of displacement at the middle here. That's the displacement magnitude 15. You can see that here it's less. And that's because this guy is taking compression. So here's looking at that same system. Now we're plotting the displacement, magnitude of displacement of that shell. It's basically getting pinched because this whole material is moving downward mostly here. You can see the deformed shape, deformation factor of 8. This is resisting. These are the structural displacement vectors. And you can see it's moving more here, less here, less here. Okay. Um, let's look at the thrust in the shell. Okay. So let's create a surface coordinate system, red, green, blue, where green is going to be Y, is going to be the circumferential direction that's going circumferentially. Then we can go and we can get the value of Ny, which is the axial thrust in the shell. Here's the idea, right? Axial thrust. Okay. And so here we're looking at the Ny and we're seeing that we're getting a larger value of Ny at the front, and then it gets less and less and less because of that pinching. Okay. Um, that's all I want to say. And we've reached the end of the talk. Thank you. I really thank you for your attention. I hope this has been helpful to you. The bottom line again, you just basically need to understand how to set the parameters. It's quite straightforward to create these things. They will automatically form those links to connect with the grid. They don't have to sit where the grid points are, and that's not relevant, doesn't matter. Um, Again, the data files and everything and this entire talk should be accessible from somewhere near where you clicked on to get this talk from. And again, you can use the discussion pane and send us some questions, and they'll get forwarded to me, and I'm more than happy to answer your questions. Okay. So with that, we're going to sign off. Have a good rest of your day. Goodbye.